Looks. Okay, we still in focus. So the question was, find the sides and angles of triangle ABC without using log sines and cosines. Since I feel pretty good with finding the sides using the Pythagorean theorem, but I didn't see any of those errors that I saw Monday from the Pythagorean theorem. That's encouraging. That's exactly what I would expect. I wouldn't expect to make that mistake. Okay. So this is 113. Start from -6,7, go -2i plus aj. I think you end up with -a15. That's your point C. You agree? All right. And then from 113 up to -815 is -7i. So I'll just make this a little vector. And I'll even call this vector for reference BC. Call this vector AB. Call this vector AC. Okay, -7i, then it's plus 2j, even though it doesn't look like it. Okay. You know, it looks like it's much further than 2 units here, but the drawing isn't necessarily representative to be taken as a schematic. Okay. So we don't necessarily your drawings are going to look like they should, but generally you'd want to make the drawing a little more representative for this arrow may be ending here, smaller angle here, so that you have an intuitive idea of what these angles might be. So a good sketch is a good idea, but if your operations are correct, even if you got a bad sketch, you're going to get the right angles. You're going to get the right results. Okay, so well. Okay, well, what is a from -6 to 1? 7. 7 to 13 is 6. So the square root of 7 squared plus 6. Okay, now plug that into a calculator, get the result, or maybe wait a little while to plug it in. I think we're combining it with another result. And BC 7 squared is 2 squared, officially -7 squared. It's legs. And AC has -2 equals the square root of -2 squared plus 8 squared. So those are numbers that you got. And you can leave them like, I mean, you can leave them like that. I don't even care if you don't square them and add them, as long as you got the right stuff down there and then use it right later. Now for convenience, it might be better to go ahead and add them and you can calculate a decimal equivalent, which is only approximate. So for example, this would be the square root of 85. Okay. And so and I'd like to take last time to improve your calculations. Then we just need to see what the angles are. Okay. Okay, we do the dot product, AB with BC. 7 times -7 is -49. 6 times 2 is 12. Right? 49 and 12 is -37. And then you have the square root of 85 times the square root of BC, which would be 53, I think. Okay. Makes sense? And you're going to get a negative. Well, you're going to get an angle greater than 180 degrees, which it certainly is. if you put B and C together with the tail at the same point, then you're going to get the angle between B and C, and that's going to be in the T-side. Okay. And clearly, these numbers are both bigger than 37. So when you multiply their square roots, it's going to be bigger than 37. So you know you've got a number less than 1, which of course you know you need if you're going to do the inverse cosine. Okay. That's going to be quite a bit less than 1. I could actually estimate it. That's about. So yeah, I'm saying that's probably about 150 degrees. If the thing was down here where it belongs, that's what you have. From the direction of B around to the direction of C. Okay. Oh, that makes sense. Question on it, if you got one, let me know and I'll pause. Okay, well, you do the same thing with the others, and that's it. So it's required. Okay. And if you're in a hurry in a test, just do something like this. Splash it out, then fill in as many details as you can. Now on a test, which is the big thing that depends on, you're not going to have a time limit, but you want to be able to do it kind of quickly and efficiently so you're not in there all day. I give a 3-hour test. Sometimes people stand there 8 hours working on it. Okay. So, and you're welcome to do that if you want, but I hate to see it taking that long. So try to learn to do the problems efficiently and learn what you really need to present, because you do need to document things. We'll talk about more about that later. Okay. So 90 degrees to rest. And this could be the loaded beam, the one with a couple of magnets in the end. 110, 105, 107 counts to the end. A couple people aren't here, so we don't have all the data. And somebody reported 48. But that seems way low. 78 seems more reasonable. Okay, so maybe recount that. Okay. Now, we want to get as 90 degrees per count and rest. Anybody reason out the angular acceleration from that information? It's actually a simple 2-step process to reason it out. You don't need formulas. For most uniform accelerated motion situations, you don't need formulas. There are 2 situations where you can. Okay. Still, you want to be able to use the formulas. Okay. Well, actually asking you to do the accelerations a little bit of a jump for today. So let's say, can you tell me what the average angular velocity was for each of these? Whoops. Okay. So again, the question, I thought I recorded, was recorded. From 90 degrees per count to rest, what's the average angular velocity? Okay. I've got one answer. It's actually kind of a good answer, but it was a little bit overthought. Okay. And then we got an answer. And if you're watching this, you should be stopping and think yourself, what is the average angular velocity? Because if you don't think through it, you won't learn as much. But anyhow, pause the video and do that. But the average angular velocity, if you assume angular acceleration to be constant, okay, is, well, Okay, that's the answer that was given, because you're going from 90 to 0, the average is 45, right? Right? And that's valid. If alpha is constant. Why is that valid if alpha is constant? Well, let's look at a graph of omega versus t. Alpha is the rate of change of omega. If it's constant, that means the rate of change is constant. The rate of change is the slope of the omega versus t graph. And that slope has to be constant, which means you have a straight line. Okay? So, reasoning is constant alpha. Constant rate of change of omega with respect to t, but I'm not writing out all the words. Desirable as it might be to do so. Constant rate of change implies constant omega versus t slope, which implies a linear graph. And right there's half the concepts in calculus. So you really have to understand that. You don't understand calculus, you don't understand that. And if you understand that, it doesn't mean you understand all of calculus, but there's a good chunk that illuminates, okay? As far as the meaning of calculus. So what we have is 90 degrees per count to 0, right? And the average of any linear function, what's the definition of the average value of a function? Okay, now I just tried without success to drag out of the class what the average value of a function is. And I commented that nobody ever remembers this. It's one of the most important things to know for calculus. You're going to think about things. Okay. You're so busy doing the operations, you stop thinking. And that's the way it is in calculus. I mean, I was the same way. Came out of calculus, and I knew this was important. I knew that was important, but it didn't mesh together until my sophomore year. Okay, when I was taking more advanced courses that took physics along with calculus. Everybody did. And then in second year physics, that's when you really had to put it together. Okay. In any case, okay, if I ask you to get the average value of x squared plus 9 between x equals 0 and 10, what would it be? Well, what do you mean by the average? Okay, you can take a bunch of equally spaced values of the function and add them up and divide by the number that you added and get a pretty close average. Okay, or you could take little slices of the region under the graph and add them up. Okay, add up the areas and then divide by the length of the interval. It turns out that's the same. Take the limit as the intervals approach 0, and you have the integral divided by the length of the interval. Now, the integral is, where do you see the integral on this graph? Well, it's the area beneath the graph. Okay. The average value is the value such that area of this rectangle equals the area through the whole graph. Okay. In this case, this is a straight line graph, and that means that this triangle, which is outside the region that you're looking at, and this triangle, which is inside the region, should have equal areas. These triangles are congruent, it's equal. It comes out to them the average value is the value at the midpoint. Now you want to flush that argument into yourself, try to understand that as best you can, because they're important insights that help you think about things that you can't think about if you don't know that. Okay? And things that might well be important in your engineering. Make it easier to understand something. Get out and practice and you understand something that other people don't, and gives you an advantage, okay? Gives you more mobility if you can do things like that. The more you know, the more mobility you tend to have in your career. Now, ask Ryan Haley about anything I say about the engineering field, okay? And I've got a grandson who's second year now is practicing electrical engineering tech graduate. So yeah, I get some feedback. But yeah, it's my grandson. It would be nice to not tell me when I'm wrong. So don't take my word for it, but consider what I have to say. Okay. End of digression. This tells us that the average value occurs at the midpoint. That's happening between here and there now. Okay, does that make sense? So once that makes sense, well, let's make sure that makes sense. Okay, so if something goes to zero linearly, then it starts with twice its average value, right? And that's the only way its average value, which would be the average of initial and final, if the graph is linear. It's the only way that the average value is going to be 45 degrees of compass. It starts at 90. Now, it's not quite linear, then that's not quite right. And then, as I said, this situation is not, omega is not completely linear. Pretty close, but not completely. Okay, now, my question is, so with alpha, if the omega t function is linear. Now, alpha is the acceleration. Okay, I got a very good answer. It said divide the 90 degrees per count by 106. Well, I said no, it's 106 counts. But yeah, okay. Now, really, if you want to write this out carefully, go ahead and write it out in symbols. Omega F minus omega naught over delta T. Okay. And delta T is just the time between this and this. T in this case is not this. It wouldn't be appropriate to use T because in this situation, T is the number of counts since we started counting. Okay. So T is running on, but this is a delta T. Okay. That makes sense? All right. Well, that equals then 0 degrees per count. Abbreviating count a little bit because I don't have room. Over I'm estimating 0.81 degrees per count. And actually 6/7. It'd be more like 85 degrees. 85 in your calculator, I think come up with close to that. And it's per count. Per count. But it's all over the board. I'm not too critical when you scatter things all over your paper. And I'm kind of used to finding them. We'll put a circle around that. There's your final calculation thing we're trying to get. And just the arithmetic of algebra. You divide a degree per count by a count. Okay, it's like a degree per count times a reciprocal count. Gives you a count squared in the denominator. All right, so now we've got this as a beam. Okay. What do you get for the unloaded beam? Punch it in your calculator, tell me what you get. Anyhow, okay. So we just determined this is the alpha here being the change in omega over change in time. The average alpha, the average angular acceleration is that 0 degrees per count minus 90 degrees per count of 106 counts, about negative 0.85 degrees per count, which is negative 0.85 degrees per count squared. Just in case you had to call it that, but you did. And it's 0.85, not 0.8. Approximation, that was the okay. So, the unloaded beam, same calculation, basically gives you a greater magnitude of the acceleration, meaning this thing's going to slow down faster than this. That makes sense? Because every count, this thing loses 1.15 degrees per count. It only loses 85 degrees per count. 0.85 degrees. Okay, here's a tricky question now. Let's say we start the unloaded beam at 90 degrees per count. And I'm going to say, how fast should the unloaded beam be started so that both stop at the same time? Now, I don't know how we would manage to start the second beam at 90 degrees per count. Okay. We don't have a mechanism to get the beam moving at a given angular velocity, and it'd be an engineering problem to create an apparatus that would do that. It'd be a little bit involved, okay? You have to have a servo and stuff and calibrate it and all that stuff. No, we're not going to do that, obviously. But theoretically, it could be done. Okay. So, how fast should it be started so that they both stop at the same time? How would you approach the problem? Okay, now if this is a lab, I give you longer to think about it. So forth. Well, the same thing you said was, one point you said when I was discussing this was Well, it takes 106 counts for this thing to come to rest, right? So that thing would have to take 106 counts. So what speed should it have come to rest in 106 counts? So because I just wrote all that out, but it takes 106 counts to load a beam. How fast should you start the unloaded beam? It's going to come to rest in 106 counts. And my question is time interval delta T, by how much does it make a change to the unloaded beam? Let me put a couple of symbols on these. Alpha loaded. So alpha sub L is loaded beam, alpha sub U is the acceleration of the unloaded beam. Okay. What do you think? Well, the answer is delta omega equals alpha U delta T. Okay. Take the rate at which this thing changes in time, is expected time, multiplied by time interval, you get the change in omega, right? Okay. Well, if, what do you know about alpha U? Okay. 8.85 degrees per pound squared, 106 pounds. All time. Wait a minute. Look the other side, get that. What Wes said was correct. Was Wes. Um, but the units, it'll work out. So somehow that seemed like a plausible result. Um, anyhow, we don't have time to draw it all together. So, think about it. Now, you're gonna have an assignment with some simple problems from chapter 3. And let's talk about uniform acceleration. We've talked about it with the angular system. Take these ideas, they work just as well for linear system. Okay. And we're going to be measuring things like the velocity of a ball down a ramp indirectly in lab next time. So, you see what the assignment is. And try to apply what you've learned here. And I'll probably append something onto the end of this video.